All right, now, if any of you needed a win, this is the chapter to get it. Okay? Well, I'm going to be brutally honest. With the exception of maybe 5 or 6 of you, I stopped feeling bad a long time ago. I had 37 people not even start the homework. No. The homework for last chapter. Didn't even start the homework. The ones that were due before the test. So it's really hard. I mean, you can see how it would be really hard for me to feel bad when you get obliterated by a test when you don't do the damn homework. I mean, that's logical, right? Okay. It was like one of those things. I'm at home, and I'm giving it, and I look at a kid's test score, and then I immediately go and look at it. I'm like, well, okay. I'm not feeling bad for you. I'm not. So, it is what it is. Now, granted, there are a few of you, and I'm going to be honest, you did exactly, like the most missed question was the dilution, M1V1 equals M2V2, right? Okay, well, what didn't you do? Anybody want to take a stab at why we all missed that question? Yeah. Yeah, you didn't add them together. None of you did. It was hands down the most missed question. And I'm like, did we not talk about that kind of problem? Yeah, we did. What, Richards? Yeah, I didn't say everyone didn't, but that was the most missed question. All you had to do is take those two values and add them together, because I know I taught that. So, it is what it is. All right? All righty, so it is 2-8 today, I believe, correct?
Yeah.
2-8. Okay. This is Chem 11:10, Chapter 9, Day 1. And the other thing is for today's stuff, I uploaded it last night. So my hopes weren't really high. But there were a few of you that did it, so good job. Yeah, so whatever. So our objective for today is going to be able to gain a better understanding of acids and bases. Now, I'm going to be honest. We do acids really well. Really well. Bases, bases not so much. Okay, I don't know why that is. We will actually watch a really cool video probably on Wednesday on acids. And we'll incorporate that into what we're teaching. But yeah, it's pretty cool. Now, what you need to understand is that the way we look at acids have changed over time. Okay, back in the day, there was a dude named Arrhenius, and I need to look this up because I always spell Arrhenius wrong, and that is this. So Arrhenius. Okay. Now, back in the day, there was what was known as an Arrhenius acid and an Arrhenius base. Okay? And an Arrhenius acid simply donated a H positive. Okay? And an Arrhenius base donated an OH negative. Now, what you need to understand is this. What it means by donated an H positive is this. If I take HCl, okay, and I add it to H2O, I am going to get out H3O positive plus Cl negative, okay? Meaning that this HCl had broken up. It had done what? It had dissociated. And it dissociates into an H positive and a Cl negative. Kind of the stuff we talked about last time. It's like a what there? What does HCl behave like right there? We talked about this last time. What kind of compounds did that? An ionic compound. So it behaved like an ionic compound, right? This is this right here. That's the H positive it donates. And that H positive can do a couple of things. One, it can just float around. It doesn't do that very often because H positives are really, really, really reactive. So what it usually does is it finds a water molecule to hang out with until it finds something else to do. This right here, this is called the hydronium ion. Hydronium ion. And that's usually how you will see that H positive written. Okay, it'll be written as a hydronium ion, which is really just a water molecule that has an H positive attached to it for right now. Okay? Now, an Arrhenius base would be something like this. You take NaOH, okay? And it's going to split up into Na positive plus OH negative, right? This is when it donates an OH negative, okay? Now, the flaw to this method, okay, and you got to understand, this is kind of the old school method. Okay, they don't really talk about Arrhenius acids and bases anymore. Okay, and the reason is that an Arrhenius base is very limited because there aren't that many compounds that can donate an OH negative. Okay, and they'll all look something like this, something OH at the end. Okay, now what happened is along the line there was two dudes, and their names were Bronsted and Lowry. Okay, and they came along and they said, well, because under the Arrhenius model, an Arrhenius base is a very small group of chemicals, which means there's not many things that we truly look at as bases. Whole bunch of acids, but very few bases. And they said, well, we gotta reevaluate that. Kind of like some of you in your test scores, okay? Now, then they came up with what's called the Bronsted and Lowry model, and it changed. Okay, in a Bronsted and Lowry model, an acid is still a proton donor. Okay? But it changed when they talked about a Bronsted and Lowry base. A Bronsted and Lowry base is now a proton acceptor. Okay? What that meant is that took the number of bases, or the number of compounds that we consider a base, and made it really big. Okay? Because there's a lot of things that can accept a proton. Okay? And so this is, you need to make sure you know what those mean. Okay? Now, typically, in every reaction, not in every reaction, but in every acid-base reaction, you're going to have this kind of setup. Okay? So let's say I take, let's look at the one we just looked at. Let's say I take HCl and I add it to water. Okay? I'm going to get H3O positive plus Cl negative. Okay? Now, every acid or base reaction is going to look something like this. Okay? The HCl is obviously my acid. And in an acid-base reaction, you always have to have one of your compounds be an acid. The other compound has to be a base, which is why they call it an acid-base reaction, right? Well, if that's my acid, what does that make my water in this case? It makes it my base. Okay? Now, from there, you are going to have what are known as conjugates. Okay? So you're going to have a conjugate acid, and you're going to have a conjugate base. Okay? Anybody know which is which here? Which is my conjugate acid and which is my conjugate base? Anybody studied this in any other classes? Nobody? Okay? So right here, what I do is I look backwards. Can I say, okay, let's say I went that way. Which one of these would be my acid? Would my Cl donate? No, my Cl would accept, right? Okay. So that makes this my conjugate base. Makes this my conjugate acid. Okay. Now, the way you look at that is this Cl did what to go over here? Didn't it accept an H positive? Right? Which would make it a base, right? This one then did what? To go from there to there, it had to lose an H positive, right? So that makes it my acid, right? Now, the other way you can look at this is the conjugate acid is what you have after accepting the H positive, right? The conjugate base is what you have after doing what? Donating the H positive, okay? And these always comes in pairs. This is my acid, that's its conjugate base. This is my base, that is its conjugate acid. And it'll work like that for anything. Let's say I take this. Let's say I take HBr, okay? I take HBr, I add it to water. What am I going to get? I'm going to get H3O positive, and I'm going to get Br negative. Well, what is the HBr? That's my acid. How do I know it's an acid? Does anybody know? It's really easy. It even better than that. It always starts with an H. No matter what, if it starts with an H, it's an acid. Okay?
What about water?
Water is an acid.
Unless it's balancing out something else.
Yes, exactly. Unless in this case it can't be. Water, does anybody know what water is? It's actually a really good question. Anybody know what water is? Nobody? Water is what is known as amphoteric. Anybody know what amphoteric means? Say it louder, Richards.
Acid or base.
It can be an acid or a base. Meaning it's going to do whatever it's got to do to make the reaction work. So in this case, it's my base. Now over here, which one's my conjugate acid? Which one's my conjugate base? The H3O positive is my Ca, conjugate acid. The Br negative is my conjugate base. Okay.
And so the conjugate acid is an acid because it donated an H positive?
Well, it accepted an H positive, but if I look going the other way, it would donate the H positive.
Oh, going the other way, okay.
You see what I'm saying?
Yeah, that makes sense.
Yeah, so it just depends on how you want to look at it. Okay? There are two different ways of doing the same thing. One is doing it this way, or one is looking at it going backwards. Yeah, Br minus accepted an H to become HBr, right? Which makes it my base, because base is a proton accepted. And when they say proton, what are they really referring to? When they use the word proton, what are they referring to? Anybody know?
H positive?
The H positive. That's what they refer to as a proton, is an H positive.
Can you move it up, please?
Yeah. That is basically what makes it an acid. Okay? Now, both of these, HCl, I'm going to put a comma there instead. So, like HCl, what the hell? Oh, it's empty. Can't make any more mistakes. I'm screwed.
There's one right here.
Oh, yeah. Good job. Alrighty, so HCl, HBr, HF, yada yada yada. These are all what is referred to as mono monoprotic acids. Anybody know what it means to be monoprotic? It has one H, right? Now H2SO4, anybody know what it's called? It's diprotic because it has two H's out front, and then there's one other one, H3PO4, and it is triprotic. And all that means is that how many H's it has on the front that could, in theory, break off. Okay, now H2SO4, does anybody know anything about H2SO4? Say what? It is created with the polyatomic, you're right. Okay, but does anybody know anything about it? Okay, it is affectionately referred to as this. It is the baddest acid on the block. And if you get the play on words, yeah, that's intentional. Okay, it's the kind of stuff that you want to hide a body. Yeah.
Yikes.
That this stuff is literally, so like you take, and if you were to like take the palm of your hand and dump some H2SO4 in there, okay, by the time you could wipe it off, it would have started to eat a hole in your skin already. You leave it on there for say an hour, you're going to be able to see your bones. You leave it on there for a day, and you will have a hollowed out hole in your hand. It would burn its way right through. I have a whole bunch of it. Yeah. Yeah. So.
What's it called?
Yeah, what's the common name for it?
It's called sulfuric acid.
Oh, okay.
And a country's wealth.
I'm just doing that too.
A country's wealth is determined by how much of that it makes.
Really?
Yeah. Yeah. Does anybody know what the GDP is?
Yeah.
The gross domestic product of a country.
Yeah.
It can be traced back to how much sulfuric acid that country makes.
That's crazy.
Yeah, it is. When we watch the video on Wednesday, you'll see what I'm talking about. It's actually really, really cool. But this is I mean, you know, they say money makes the world go round. I'm not sure that's entirely true. Okay, this stuff right here is used in almost every industry in the world in some way, shape, or form. So yeah, it's kind of cool. You know, it's all chemistry. That's what I tell people.
How is it used in medicine?
In what?
Medicine?
It will kill everything.
It's like a sterilizer.
You want to sterilize something, you stick it in that.
Okay.
Like it's funny, but in the video they actually talk about the beer industry. And when you're done with the vat, same thing with the wine, any of those things, I need to clean a big tank out. They just fill it with water and dump a little bit of that in there, and whatever's in there is now no longer in there. It's dead. Yeah, Criddle.
Do we ever do a lab with that?
We actually do. I dilute it quite a bit. But you got to understand, it's like that bottle. It's kind of interesting. That bottle in the left-hand corner, that's concentrated hydrochloric acid. That is as concentrated as it gets. Do you see how that bottle looks? That's from just the sheer corrosion that is doing to that bottle. Now, sulfuric acid, if you were to put that in that plastic bottle, it would take that bottle and just melt it. Okay, so a few years ago, this is one of my favorite stories, I bought a bunch of really nice plastic containers to put chemicals in because I mix so many chemicals up, right? And in the reading on the website I bought them from, I obviously didn't read very carefully, and it just said safe for acid storage, right? Well, in parentheses below that, it said dilute acid storage, right? Which means you've already watered it down. So Mr. Riley was getting ready to do a lab, and he put some concentrated sulfuric acid in one of these bottles. And when he came back, so he had him in a cart. Our cart had like this high of rails on it, right? And so he put his entire lab in there. So he was gonna wheel it out into his room. When he come back, the bottle that he'd put it in was gone. And it had ruined the entire lab because it had eaten its way through the bottle and then proceeded to destroy everything in the cart. Damnedest thing I'd ever seen. Literally, I couldn't believe it. He picked up, and all that was left was the lid. It had just destroyed the entire bottle, and then it proceeded to destroy every chemical in the cart.
What was the lid made out of?
Well, the problem is the lid was just kept up. So as it ate the bottle away, there was just, it was crazy. I'd never seen it. So I immediately come in, I call the company and go, hey, I don't know what you're selling. And she goes, well, you probably need to go. So I went back and reread the fine print, and sure enough, it said dilute, and they put concentrated in it. It's like when they ship that stuff, it comes in glass. It's got a special lining in it. It's actually really cool, but you're talking nasty stuff. So, but to a science geek, it's way cool because of the things you can do with them. Like, you want to etch glass, that's what you use to etch glass. It will eat pretty much, there's like 2 precious metals that it won't eat. It won't eat gold and it won't eat platinum, I think. Are the 2 it won't. But pretty much anything else you put in there, there will be nothing left of it over time. So, kind of crazy, but it is what it is. So acids are way cool. Okay. Alrighty, now from there. Alrighty, so there's 2 ways that they talk about acids. Okay. We will mainly talk about molarity again. Okay, so those of you that understood molarity will remember molarity is what? Yeah, moles of solute over liters of what? Solution, right? So like that hydrochloric acid back there is like 12.3 molar. And that's as concentrated as you can get it. Which means there's 12 moles, 12.3 moles in 1 liter of solution. That's a lot. I mean, a lot. Sulfuric acid, you can get to 16 molar, which is a lot. Which is why, plus it's diprotic, which means basically you get what?
Oh, you get 32 more.
You get 2 for the price of 1. Yeah, which makes it just, like I said, the baddest acid on the block. Okay, but then they also talk about them as what is known as strong versus weak. Okay, now a strong acid has nothing to do with its molarity. Okay? It has to do with what? Think electrolytes here. Does anybody remember what a strong electrolyte was? Say that louder. Yeah, so a strong acid, and this works for acids or bases, if they use the term strong, it means it completely dissociates. Okay, if they use the term weak, that means well, how else? If it's not completely, it must only, I heard it, partially dissociates. And we will actually calculate this down the road. Okay, partially dissociates versus completely dissociates. Now, what they will introduce you to is what is known as a K value. Okay, a K value, and it usually has a Ka or a Kb. And this is the K for an, what do you think the little a means? Acid. This is the K for a base, right? The higher the K, the higher the dissociation. Okay? So what that means is that, and it's kind of relative, if I were to compare them. So really anything higher than 1 would be something that tends to dissociate a little bit, right? But the bigger it is, the more it dissociates. It's like if I had only 2 K, like let's say I only had 2 things. And one had a K equal to 1,000, and one had a K equal to 10. Which one is stronger? The 1,000, because it dissociates more, right? So this one would be stronger, this one would be weaker, comparing the two. Do you know what I'm saying? You got to be able to compare things. Okay, if I had a K equal to 0.0001, this is definitely going to be quite what? Quite weak. Meaning it doesn't do what? It doesn't dissociate. It has nothing to do with what kind of acid it is. Okay, it's simply a weak acid, meaning it doesn't dissociate. We will learn some specifics. We should already know probably 3 that I've talked about that are strong acids. Okay, and what are the 3 I've already talked about? Sulfuric acid, H2SO4, HCl, and HBr. Those 3 are all strong acids. There are, depending on the book, there are 6 or 7. And then they also have strong bases, which depending on the book has 5 or 6. I will give you a list of them just so you have them. Okay, not today, but we will. We will get there. There is a, you know what, we don't need that right now. There is a book, or there is a chart on page 320 in your book, which does go over this a little bit. But I don't think we need that today. No, in fact, I know we don't need that today. Alrighty, now, KW. Okay, KW. This is what is referred to as the K of water. Okay, and what you end up with here is the KW is 1 times 10 to the negative 14th. Now, and what this is this is just a value you need to know. You need to know that KW is 1 times 10 to the negative 14th. Okay? What that is this. That is your H3O positive concentration times your OH negative concentration. Okay? That times that will always be this. And anytime they use brackets, remember, brackets equals concentration. Typically, how do we measure concentration? Molarity. Typically, this is in molarity. Okay, the molarity of this, the molarity of that, that's how they're going to do things. Okay? So just make sure you understand that when they talk about concentration, it's typically going to be in molarity. Okay, and that should be something we've already talked quite a bit about. So just understand that. Now, what they're going to do is they're going to introduce you to pH. Does anybody know what pH is?
This is the only thing I know.
This is the only. Well, then we have some common ground here, right? Does anybody besides Springer know what pH is? Yeah, Criddle, what is it?
I don't know what it is,
but you've heard about it,
yeah.
Right? Do you know what it is? What is it?
Isn't it the level of acidity that?
Okay, it's a what? What would we call it? It's a scale, right?
Because I know it's 7 point something is
Okay, so does anybody know what the scale really goes from and to?
0 to 14.
So in theory, they say it's 1 to 14. That's not entirely true. Okay? It actually can go from 0 to 15, and actually you can get a little bit outside those numbers, depending on what it is you're talking about. Now, where does pH come from? Does anybody know? Some of you that are in secondary math 3 will automatically recognize this. Okay? The pH is equal to the negative log of the H3O. Yeah, you see how I tied that right in to something you're learning in another. Why you giving me that look, Iverson?
I don't know.
You know what I'm talking about, though, right? How many of you have seen logs in your secondary math 3 class? Yeah, you're welcome. Okay? Now, this is a simple calculation. Okay? All you have to do to find the pH is you've got to know the concentration of H3O. Now remember, you'll see it written like this. Sometimes you will see it just as H positive. Okay? Now, when I used to teach regular chemistry, this is how they wrote it. Just H positive. Once I started teaching this class, they always write it as this way. But you will see it sometimes interchanged because sometimes they do get lazy. So what they'll do is this. Is they'll say find the pH of a, and then they'll give you a what? But a what? You're right, but they'll give you a molarity of something, right? So say find the pH of a 1.4 times 10 to the negative 3 molar HCl solution. Okay? Well, let's look at this. Where does that go? That's going to go right there. So I'm going to have pH equals the negative log of 1.4 times 10 to the negative 3. $2.8. So 2.8. Now, here's my question. Yeah, so how do we, with logs and you know what I'm saying? So what I do is this. They got 2 digits out here. I'm going to go with 2 digits down here. Does that make sense? Kind of going back to what I taught early on, right? What they give me in the problem, have that dictate what I have in the answer. And I would have a pH of 2.8, right? Now,
It's 9 because it was 8.5.
2.85, so we'll go 2.9. Now, here's my question. So where would this pH fall? In the acidic range, because an acid goes from 0 to 7, right? And then from 7 to 15. This is an acid. This is a base. Now, this is the kind of question that gets everyone. Does that make it a strong acid? Okay, now listen, understand. What did I tell you I was going to do? Anybody listen to what I said about 8 minutes ago? I said I was going to give you a what? A list of strong acids, right? pH has nothing to do with acid strength. Acid strength simply means does it what? Completely dissociate or not. Okay? Now it has a fairly low pH, but that has nothing to do with whether or not this is a strong or a weak acid. Do we understand the difference? Is this a strong acid? Yes. But how do I know it's a strong acid? Because it's HCl, and I've already told you that HCl is one of those strong acids. Remember, pH does not dictate strength. I like that. pH does not dictate strength. Okay? What it is, there's 6, 7, depending. Okay. Now, this has a fairly low pH, but nothing too out of control. Okay, you've probably eaten things with the lower pH than that. Okay, not a ton of it, but it would burn. Okay, when I chug a Mountain Dew, why does my throat burn? No, because of the acid that's in the pop. Okay, it's kind of crazy. All pop has acid in it, which is why it's bad for your teeth. You'll actually, in the video, you'll see something that's brutally disgusting. And, you you'll never eat Jell-O again.
Oh, I love Jello.
Oh, me too. I still eat it. It's okay. What, Buxton? Oh, I love Jell-O. Yeah. Hey, you don't realize how many things Jell-O's in either. Yeah.
It's a Utah dessert, you know.
It's definitely a Utah dessert, but yeah, it's kind of crazy. Now, here's my question, okay? Does anybody know what pH plus pOH equal? It's similar to that, though. pH plus pOH is 14. Okay? Because this comes from what? KW. KW is H3O positive times OH negative, right? And that is 1 times 10 to the negative 14. Well, look. Okay. And if you remember, if I want to condense or expand a log, what does addition correlate to? Multiplication. Yeah. Now some of that stuff that one of your other teachers have been trying to teach you might make a little sense. Now, here's what happens, okay? So what they're going to do, and they're going to do there's 8 different ways they can ask these questions, okay? And this is what they'll do. They'll say, find the pOH of a one. No, I'm going to change that. I'm going to do a better job of changing these numbers. Of a 4.7 times 10 to the negative 5 H3O positive concentration solution. Now, this is once you get the hang of it, this should be easy. Okay? Remember how I said we should get a win? This test should be a win. Look, what is wrong with this and that? Anybody know? Yeah, they're not. This is H positives. This is OHs. I cannot go from there right to there. Okay? Now remember, pH is equal to what? It's the negative log of that, right? 4.7 times 10 to the negative 5, correct? Okay, so what is my pH then? What? 4.3? Anybody else get 4.3? Yeah? Okay. But it didn't ask me to find my pH. It asked me to find my pOH. Well, how do I find my pOH? I take 14 minus my pH, which is 14 minus 4.3, and I'm going to get what? I'm going to get 9.7, and that is now my pOH. Now, what if I did this? What is my OH negative concentration? Iverson, you got an idea?
Well, I was looking at the KW.
Oh, wow. Yeah. So what's your idea?
Well, you could put that in because you have the H3O positive.
I've got this, right? So he says that KW, again, was H3O positive concentration times OH negative concentration, right? And what was KW? What was the value? It was 1 times 10 to the negative 14th, right? Well, if this is my equation, I've got to know how many of them. I got to know at least one of these because I already know that, right? Well, couldn't I take that, substitute it in there? So I got 4.7 times 10 to the negative 5 times OH negative yields 1 times 10 to the negative 14th, right? What would I do, Iverson?
You would just, you can divide across.
Yeah, just divide across. I got 4.7 times 10 to the negative 5. 4.7 times 10 to the negative 5. They're gone. That's going to give me my OH negative concentration of what? Anybody else get 2.1 times 10 to the negative 10? Yeah? Now, let me show you what else you could have done. If you go back up here, okay, those of you that are in secondary math 3, watch. Okay? Now remember, if this is pH, right, wouldn't POH be the negative log of the OH negative concentration? Right? Right? And didn't we know what POH was? Wasn't POH 9.7? So I have 9.7 equals the negative log of this, right? Anybody know how to do that? Nobody knows what around the world is? You go base raised to your answer is equal to the number. Where that comes from is this. Log base number answer. Change of base. So I'm going to go base. Well, what base is written right here? 10, right? Problem is this is the negative log. So I'd divide by a negative. And I'd go 10 to the, take 10 to the negative 9.7 for me and tell me what you get.
2.0 times 10 to the negative
2.0 what?
10. It's 1.99.
Okay, so 2.0 times 10 to the negative 10th. Notice how what? How close we are. So yeah, and you can do it either way.
Wait, so like on the test then?
It won't matter.
It wouldn't?
Because remember, it's multiple choice, right?
Yeah.
So you're gonna, I would assume that whatever you do, I'm trying to remember, I haven't done all these calculations on the test yet, but I'm pretty sure it's not gonna matter. They wouldn't put two answers that close. Okay? So yeah, so usually all you have to do is, if you want to know, like if I wanted to know this, you simply go 10 to the negative POH, and that gives you the same thing. Okay? Different way of doing the same thing. All right. That's enough for today. You need to get 1 and 2 done for sure. There are 4 Learn Smarts. We're going to cover this in 3 days, though. So kind of plan accordingly, okay? Okay, get busy. Those of you that have not taken the test, that needs to be done ASAP, which stands for as soon as possible.